directional derivative and the gradient, both what they mean and how to find them. If we draw ourselves an example, let's say that we have some surface S, and that surface is defined by z is equal to some function of x and y. Here's what we can do with partial derivatives so far. First, we can find the instantaneous rate of change. In two different directions. So the direction of x when you keep y constant, and then the instantaneous rate of change in z when you change y but keep x constant. We also can find the slope of the tangent line. That is parallel to either the x or y axis. Okay, so how that looks on our figure, let's say that we choose some point. And let's say that point has coordinates x naught, y naught. First thing we can do is we can pass through a plane that is parallel to the x-axis. When we do, we're going to get some line like this. That's partial z, partial x. And then we pass through the other plane the other way to get partial z, partial y. Now, while those are helpful, that's pretty limiting. It's not often that we're going to be going in just these two specific directions. We might be going in a different direction instead. So that's what we're going to talk about today, is what happens if we're heading in some other direction that we're going to call u. So we want to know what is the rate of change in z as we head in this direction u. So what if we want to go in other directions? Here's our plan. We have some point, which we're going to call P, which has coordinates x naught, y naught, z naught. And we have some direction u, which is AB. So we have that on our figure. We have this direction u, we have that point. First thing that we are going to do is we are going to pass a plane through the surface. That plane is going to be vertical, and it's passing through u. Can you picture what I mean here? Passing some plane through vertical from u, and it's going to pass through your surface and leave a line. So then, slope of the tangent line is going to be the rate of change of z in the direction of u. So that's ultimately what we're looking for, so we need to figure out how to find the slope of that tangent line. So here's what we're going to do then. We are going to choose another point, Q. We're going to call that point XYZ. that point has to be on both the surface and the plane. So we pass this plane through. It's going to give us some line, some intersection between the surface and the plane. We're going to choose some point that is on that intersection. And then what we're going to do is we are going to project P and Q onto the XY plane. So this is going to be the notation for our projection of P. That'll be x naught, y naught, and then 0, since we're on the XY plane. Likewise, Q will be x, y, and 0, because we're on the XY plane. Okay, we're almost there. I want to show you a picture, though, of what this looks like before we finish. Okay, so this blue is the surface. We have some point. We have some direction, u. So then we have this vertical plane that's going to be passing through u that we pass through the surface. And it gives us this line right here. I guess not really a line, this intersection, this curve C. So we choose some other point Q that is on both the plane and the surface. And then what we did is we projected P and Q down onto the XY plane. So what you can see is that they lie on our direction vector u. With me so far? Okay. So like I said, we're almost done with getting to how we actually calculate this. Okay, so like you saw on the figure, if we connect those 2 points, the projections of P and Q, that is going to be parallel to u. Parallel to u, but not necessarily the same length. So those 2 points are going to fall on u, but they're not going to be the same length as u. So what we know is that that vector PQ is u multiplied by some constant h. And u was AB, so if we multiply by h, we get the components then of HA and HB. Okay. We know that the coordinates of point Q, that x, is going to be x naught at HA, and y is going to be y naught at HB. So then what we get? The change in z over h. That's z minus z naught over h, which is f of x naught plus HA, comma, y naught plus HB, minus f of x naught, y naught, all over h. And lastly, what we are going to do is we are going to take the limit as h goes to infinity to obtain the rate of change of z in the direction of u. Okay, this leads us all to our definition. The directional derivative of f at the point x naught, y naught in the direction of a unit vector u with components a, b is as follows. Here's the notation. So this is the directional derivative of f at some point in the direction of u. And this is going to be the limit as h approaches infinity of that quantity that we wrote before. And that is, of course, if this limit exists.
Is approaching 0 or infinity?
0. Thank you. Sorry, this h should be a 0. Okay, and this is going to have the same meaning as any other derivative. So this is going to tell us the rate of change of z in the direction of u. Now, you need to know this definition. This is not the definition. We're not going to use the definition, though, to actually calculate the directional derivative. So we're going to do a quick example, and then I'll show you a theorem that'll make calculating this much easier. Okay, any questions about the meaning of the directional derivative? We're not talking about calculating yet, but anything about the meaning? Okay, we're going to do an example in your book. I'm just going to put it up here because I don't want to redraw the figure. Sound good? Okay, great. Okay. So use the weather map in figure 1 to estimate the value of the directional derivative of the temperature function at Reno in the southeasterly direction. Okay, so what this is asking, as we head in the southeasterly direction from Reno, what is the rate of change of temperature? Temperatures are z. What is this an example of?
Contour.
Yeah, contour map. Okay, so what we're going to do is you're going to draw in the southeasterly direction. And you need to know what was the temperature, where is it going? If you look at this level curve right here, temperature's at 50. Next level curve you get is at 60. With me? So that means as you're heading in the southeasterly direction through Reno, there's a temperature difference of 10 degrees. Good so far? Okay. Other thing you need to know is how far you've gone. So you're going to look at from this point to this point. How far was that? How many miles? It's about 75 miles. So this is the answer that you get then. Temperature difference of 10 degrees. Over 75 miles gives us 0.13 degrees per mile. Get the idea of a directional derivative? Okay, so I think you have one in your homework like this. This is not practically how we're going to be doing it, though. I think you have one. Okay. So let's talk then about how we're actually going to be calculating this. So this theorem will tell us how to calculate the directional derivative. If f, not if, f has a directional derivative, in the direction of a unit vector, thank you, Alex. Hi. Oh, she's come in. Okay, here's how you're going to calculate it. You are going to take the partial with respect to x at that point and multiply it by a. And then you are going to take the partial with respect to y at that point and multiply by b. That's in 2 space. 3 space, it's going to be the same idea. You would take the partials with respect to x, y, and z. So let's do an example. We are going to find the directional derivative of f at the point 1, -2, 0 for the function as follows. X squared y, subtract yz cubed, add z, in the direction of a, which is 2I, add j, minus 2k. Okay, so using this theorem above, we're going to need to take the partials, and we're going to need the partials at that point. So the first thing I want us to do is find all 3 partial derivatives, the partial with respect to x, partial with respect to y, and partial with respect to z. So in this case, we get 2xy is our partial with respect to y, or x rather. Partial with respect to y will be x squared, subtract z cubed. Partial with respect to z will be -3yz squared plus 1. Then we are going to evaluate each of these at 1, -2, 0. If you trust me, I will tell you they end up being -4, 1, and 1. Okay. What do we have to do before we can start plugging numbers in? Are we allowed to use this direction right away, or are we ready to use it right away? Has to be a unit vector. Yeah. So we need to find our unit vector, which is going to be that direction vector A we have divided by the norm of A. So we have 2, 1, -2. The norm is 3. Is it okay that I just tell you that? So this ends up being then 2/3, 1/3, and -2/3. So then our direction vector at the point 1, -2, 0, or our directional derivative, partial of x at that point times a, so that'll be -4 times 2/3, plus partial of y times b, so 1 times 1/3, plus 1 times -2/3. So we get -8/3, -7/3, -9/3, so -3. So then I want to make sure we know what that means. This tells us for every unit we travel in the direction of A, f is decreasing by 3 points. Does that make sense? Every unit we travel in the A direction, f will decrease by 3 points. At that point, as soon as you get away from that point, it's going to change.
So you're always finding it like at a specific point?
Sometimes you'll just be asked to find the general directional derivative. Most of the time it's at a specific point. Okay. You guys are going to do an example now. We are going to find the directional derivative if our function xy, f of xy is x squared e to the -y. And u is the unit vector that is given by an angle of theta equals 2 pi over 3. I also then want to know what is the directional derivative at the point 1, 0. Okay, so take, I don't know, 3-4 minutes and do this problem, please. If you need any assistance, check with the person next to you. Can you check in with the person next to you and see where you all are? Do we have an idea of where we're going, or have we gotten stuck? We're good? Do we need another minute? Do we need another minute? No, we're good? Okay, I'm just going to show you my work. So I got this to be the general directional derivative, and this to be the directional derivative at our point 1, 0. You should have found your unit vector using that angle. You should have found your two partials, which give you the general directional derivative, and then you plug in your point 1, 0. Did you guys get the same thing I did? Beautiful. Okay. How do we feel about the directional derivative? Not bad? Great. So we're ready to talk about the gradient?
Yes.
Okay. Can I move this? Okay. So next thing up is the gradient, which is related to the directional derivative. Okay, so here's what we've already done. directional derivative in the direction of u at some point xy is the partial of x at the point xy times a plus the partial of b, or partial of y at xy times b. So what we're going to do then is we are going to re-express this. So we're going to write it in a different form. Another way to write this is as a dot product. So we could have the partial with respect to x at our point xy, and then the partial of y at xy, dotted with some vector ab. That vector AB is just our unit vector u. This vector here, that first one, that's called the gradient. So the gradient, you're taking all the partials. Okay, so this is going to lead us to our definition. If f is a function of x and y, then the gradient is defined by okay, here's the symbol for a gradient. So that's the symbol. So we take the gradient of f, and that's the partial with respect to x times I, and then the partial with respect to y times j, or written in bracket notation So this helps us with the directional derivative, or helps us write the directional derivative a different way. Directional derivative in the direction of u of the function f at some point xy. That's really the gradient of f at some point dotted with the unit vector. Now, there is more that's important about the directional, or about the gradient rather. It's not just that we can re-express the directional derivative. So we are going to do an example, and then I'll tell you more about why the gradient is important, but it does have some use for us. Questions on the gradient before we do an example? Okay. Consider some function f of x, y, z is x sine of y, z. In part A, we are going to find the gradient of f. In part B, we are going to find the directional derivative of f at the point 1, 3, 0 in the direction of u, which is 1, 2, negative 1. Okay, if we go to find the gradient of f, similar idea to what we wrote above, except in 3 space. We're going to have to find the partials with respect to x, y, and z. So our partial with respect to x will be sine of y, z. Partial with respect to y, you'll have to multiply the z out because of the chain rule. So we get xz cosine of yz. And then the partial with respect to z, multiply the y out from the chain rule, so we'll have xy cosine of yz. So that's the gradient. If we go to find the directional derivative, we're going to have to make this direction a unit vector. So that's the first thing that I'm going to do. The norm of that u will be the square root of 1 plus 4 plus 1, so the square root of 6. So then the vector we're going to use is 1 over root 6, 2 over the square root of 6, and negative 1 over the square root of 6. Finally, we can calculate the directional derivative at our point 130. That'll be the gradient at the point 130, dotted with our direction. Before I wrote u, but in this case u is not a unit vector, so I'm going to write it as a unit vector. If I plug in 130, I get sine of 0, which is 0. Up here I get 0 times cosine of 0, so that's 0. And up here I get 3 times cosine of 0, which is 3. So it ends up being negative 3 over the square root of 6. If you want to leave it like that, that's fine, but that's an easy one to rationalize, so this ends up being negative root 6 over 2. Okay. Okay with the gradient? Do we see how it relates to the directional derivative? Okay. Does our brain have a little bit more in it for today, or no?
Yes.
It does? Okay, it relates to the gradient again, so I'm not changing a whole lot on you. Okay, so I told you the purpose of the gradient is not really to rewrite the directional derivative. That would be a waste of our time, but it actually has some important value. So this next theorem is going to tell you the importance of the gradient, or another importance of the gradient. Suppose f is a differentiable function of 2 or 3 variables. The maximum value, instead of value, sometimes you'll see slope, the maximum slope of the directional derivative. So the maximum value itself is the norm of the gradient. And it occurs in the direction of the gradient. The minimum slope is going to be the norm of the gradient, but the opposite value. Also, something important to know. If the gradient at some point xy is 0, this should be fairly intuitive, then the directional derivative at that point is going to be 0 in all directions. Again, this is at some specific point xy. We're going to do one example, and then this will be the last one for today. Suppose that the temperature at a point XYZ in space is given by the following function. T of XYZ is equal to 80 divided by the entire quantity of 1 add x squared, add 2y squared, add 3z squared, where T is in degrees Celsius and x, y, z are in meters. In which direction does the temperature increase fastest? At the point 1, 1, -2. And then what is the max rate of increase? Okay, so we have some function that gives us the temperature at a point in space. We want to know in which direction is the temperature increasing the fastest, and then what is the maximum rate of increase. Based on the theorem that we just wrote down, the direction is going to be the gradient. So our gradient in this case, we're taking the partial with respect to t of x, y, and z. Okay, so our gradient of t then. If you picture that entire denominator to the negative first power, you'll bring that -1, so you'll have -1 times 80 times the derivative in the denominator with respect to x, which will be 2x, over that 1 plus x squared plus 2y squared plus 3z squared, the entire quantity squared. Same idea here, you're going to bring the -1 down, and you'll get -80, this time times 4y. So you'll get -320y divided by that entire denominator squared. Then you'll bring the negative, and this time a 6y rather. So you get -480z over that entire denominator. Okay, I'm going to clean this up a little bit by factoring out 160 divided by that whole denominator. That leaves us with -x, -2y, and -3z. Okay, so then what we want is we want the gradient at the point 1, 1, -2. Can I just tell you what it ends up being after you plug in those numbers? Ends up being 5/8 times -I, subtract 2j, add 6k. So then the temperature increases the fastest in the direction of the gradient. which is that answer that we got above. So that's one way that you could see the answer. It's also possible to just get rid of that constant and leave your answer as -I subtract 2j plus 6k. This is no longer the gradient, but it has the same direction. It's just a different length. So then our maximum rate of increase is the length of the gradient. This time, make sure you actually use the gradient. So it would be 5/8 and then the square root of 1, add 4, add 36. So that's 5/8 times the square root of 41, which is about 4 degrees centimeter degrees per meter. If I was asked you where is the temperature decreasing the fastest, you would take the gradient and switch all the signs. And that would be decreasing the fastest. And then it would be negative, whatever this is. Any questions on the gradient or the directional derivative? Okay, no questions on anything we've done today.